So we're dealing with sequences right now. Going into some detail on sequences. And those sequences have characteristics. They have properties. And these properties should look really familiar to you based on the properties that functions have. So there should be no surprises because a sequence is a function. And all we do, we just want to come up with a couple of definitions here. We are going to describe a sequence as increasing if the values in the sequence are going up as you move from term to term. So this just says the next term is bigger than the prior term. That means it's increasing. Decreasing, same idea, right? Decreasing. The next term is less than the prior term. It's decreasing. But it's got to be true all the way through. All right, so for decreasing, you should be visualizing a sequence that is going down forever. Increasing, it should be going up forever. Now we've got these two weird oddball ones. So the oddball ones right here, non-decreasing and non-increasing. Non-decreasing means it's not decreasing. So it is either increasing or going flat. So increasing or being constant. Non-decreasing, increasing or flat. So non-decreasing, you're imagining that it's going up or staying the same. So something like this, I'm doing non-decreasing, so it's not going down, but it can go totally flat for a while. So that is non-decreasing. Not increasing, but it is non-decreasing. And same thing with non-increasing. Non-increasing means it's not going up, so it's either staying flat or going down. Either decreasing or flat in spots. Now, when you look at the theorems, 99% of the time, it is totally fine just to replace these two words with decreasing or increasing. In a lot of math books, they try to get as general as possible, so they'll start using words like non-decreasing and non-increasing. But it's really hard to create a sequence as a function that's going to have flat spots. How many graphs did you make in algebra that went up and went totally flat and then went up again? None, right? So it is totally fine to replace non-decreasing with increasing and non-increasing with decreasing. It's going to work just fine. Because the only way you're going to create something like that most likely is with a piecewise defined function. And we're not really dealing with those right now. Okay, and then we have one other word that's probably new, monotonic. And monotonic just means that it's either trending up or trending down. So it's not oscillating. It's not doing up and down. It's staying flat and going up, or it's staying flat and going down. But it never reverses direction. If there is some increasing piece of it, it stays increasing or goes flat. So monotonic means it's going in one direction. And then we have these words bounded above, bounded below, and bounded. So I think those are self-explanatory. A sequence is going to be bounded below if it never goes below a certain y value. Be bounded below. It's got a floor, so the sequence values are all above it. If it's bounded below, it's going to be bounded below by an infinite different. There's going to be an infinite number of numbers that could be a lower bound. A lot of times, if we imagine a sequence, we want to figure out what the bound is that's the closest. So that would be called the greatest lower bound. And similarly, if we have a sequence that's bounded above, there's a ceiling that the points never go through. And same thing, if there's an upper bound, there's an infinite number of upper bounds, but we're usually interested in the least of all the upper bounds. And if we say a sequence is bounded, we mean it's both bounded above and bounded below. So if we say bounded, we mean it's trapped in a tunnel. It's got a floor, it's got a ceiling, and it's somewhere in between. If we want to be explicit, if it's only bounded above, then we have to use bounded above. If it's only bounded below, we use bounded below. But if we say bounded, it's bounded on both sides, top and bottom. It's in a tunnel. So, terminology. So here we have the red sequence. It's decreasing, and it's bounded below. The black sequence is bounded above and increasing. And with both of them, you could say they are bounded. Like with this decreasing sequence, it's more interesting to focus on the fact that it's bounded below. With this increasing sequence, it's more interesting to focus on the fact that it's bounded above. Because if it's bounded and it's monotonic, that means it's going to have a limit. So if it's bounded and monotonic, it will have a limit. Which we'll get to in a minute. We'll have a theorem that shows why that's true. Both of these sequences, if you look at them, you should be able to do these limits in your head now. They both converge to 1. If we take the limit of each of those, 1 over n goes to 0, and then you add 1. Geometric sequence. So we've talked about geometric sequences already the other day. We know a geometric sequence, if the base r is the base there, r to the n, that's a geometric sequence. If the base is under 1 in magnitude, less than 1 in magnitude, we know that that geometric sequence will converge to 0. Right? 1/2 to the n converges to 0. When you take a number that's truly a fraction, a proper fraction, you multiply it by itself, it gets smaller and smaller and smaller and smaller, or to 0. And if you take a geometric sequence and you take an r value that is greater than 1 in magnitude, it's going to, let's see, where am I at here? If it's greater than 1 in magnitude, so over here, it's going to diverge. If you take, so this is funny here. It's not that interesting, and we're not going to look at it too carefully. Do you see that if you plug in r equals 1, it's going to converge to 1? Because then it's just a constant sequence, 1, 1, 1, 1. And if you go greater than 1 or less than or equal to -1, which it's easy just to encapsulate that as the magnitude is bigger than 1. If the magnitude is bigger than 1, it's going to diverge. And they're just calling out with this little equal to also the weird scenario where if you plugged in -1, it's just going to oscillate. -1, +1, -1, +1, and that's divergent. All right. So typically when we think of a convergent geometric sequence, the constant case is not interesting. We are dealing with magnitudes that are less than 1. 1/2 to the n, 1/3 to the n, 9/10 to the n, whatever. So this picture just shows that we diverge. If we're less than -1, greater than 1, we diverge. And we're only going to converge in this little region here. Pictures of 1/2 to the n, 1/2 to the x is the continuous function that 1/2 to the n is part of, or 1/2 to the k, whatever letter we're using. And you can see that, once again, we've talked about this. As long as the base is less than 1, it's going to converge to 0. Even if you throw in a switch and you have an alternating geometric sequence, that's also going to converge if the base is less than 1 in magnitude. And then a couple where the base is bigger than 1 in magnitude. So 1.1, it's bigger than 1, it's going to diverge. Here, also base bigger than 1, so it's going to diverge. This one is just diverging with oscillation also, because there's a switch. So your sequences, you should be visualizing just a bunch of dots that are going up or a bunch of dots that are going down. And if they're going down, hopefully they're converging to something. If they're going up, hopefully they're converging to something. Yeah?
For this, do you want us to say like divergence, or do you want to say like towards infinity or towards negative infinity?
Well, if you use the word limit, usually we will say the limit is infinity, or the limit, if it's oscillating, we would say does not exist. If the limit is, we just have to be careful, because all these limits that are equal to infinity, equal to negative infinity, they don't exist. But if they don't exist, and they don't exist because they're getting bigger and bigger, then we want to say equals infinity. So there's a difference. Usually we're going to say the limit of a sub n, or the limit of whatever, equals. It depends on how the question is worded. Sometimes you write infinity, and sometimes you just say averages. It's going to depend on how the question is asked. We'll see both. Squeeze theorem. You should have seen this in Calc 1 with functions. If you've got some upper bound and some lower bound, and those two sequences are convergent to the same number, so they both converge to L, well, if we have a sequence that's sandwiched in between them, the black sequence, it must also have a limit of L. So if the upper sequence converges to L, the lower sequence converges to L, then the middle sequence, the one in between, has to converge to L. No big surprise. Same as in Calc 1 with functions. All right, so here's how the squeeze theorem works. We have talked informally about it already. We have said that the limit of something like this is going to be what? Arctan n over n as n goes to infinity. What's that limit going to be? 0. Now, to formally prove it, we do have to use the squeeze theorem. Like, we've been using just kind of some informal concepts that if the numerator is just, wobbling around between some values and the denominator is getting large without bound, the fractions must be going to 0. We've been doing that more intuitively than formally. Well, here's how we formally would do it. We're going to start out with our bounded function. So tangent inverse of n is always bounded by negative pi over 2 on the bottom, pi over 2 on the top. That's a bounded sequence. That's true no matter what. No matter what you plug in for n, that is true. And now what we're going to do is create this a sub n over here. We're going to divide through by n so that we have that. And that's going to lead us to taking the limit of everything. Take the limit of all sides. So we're going to take the limit of, we can make that minus pi over 2n if we want. We're going to take the limit as n goes to infinity. That's going to be less than or equal to. We'll take the limit of this. Usually we're going to refer to this as a sub n. So I'm just going to shortcut my notation here and just call it a sub n. And this will be less than or equal to the limit as n goes to infinity of the right-hand side, that thing, pi divided by 2n. Well, now those bounds, the left and the right, the left bound here, the lower bound, if you will, that limit is what? 0. Because now we literally do have a constant in the numerator, and the denominator is growing without bounds, so those fractions go to 0. Similarly, on the right, so we have that, so therefore the limit of a sub n must be 0. So there's how we get our conclusion. So that's how we prove those things with the squeeze theorem. The squeeze theorem is like the only theorem that we're really going to use. I mean, we will use the geometric series sum, but that's not really considered a theorem. But we'll do that actually in a minute. So squeeze theorem is probably the only theorem we'll do. So same idea with this one. What is cosine bounded between? Negative 1 and 1. So we know that this is true, that cosine of n, no matter what, we have that fact. It's got to be less than or equal to positive 1, greater than or equal to negative 1. And all we do is build the expression that is a sub n. So we're going to divide everything by n. And then we're going to take the limit of all three pieces here. And once again, we have this scenario here. Limit as n goes to infinity of a sub n. Trapped between 0 and 0 means the limit of a sub n is 0. So therefore, the limit of a sub n is 0 as n goes to infinity. So that's the squeeze theorem. So squeeze theorem, you apply it when you have a numerator that's wobbling. It's oscillating. But it's bounded. So you've got a bounded numerator. Now, when we have a situation where our sequence is monotonic and it's bounded, there must be a limit to that sequence. So this sequence on the left here is bounded. More importantly, it's bounded above and it's increasing. So if an increasing sequence is bounded above, it's increasing. That means it keeps getting closer and closer to that bound. So any bounded monotonic sequence has to have a limit. It's got to converge. Similarly, the one on the right is bounded, but more importantly, it's bounded below, and it's decreasing. So if it's decreasing and bounded below, it has to have a limit, so it converges. So if you can show that a sequence is increasing or decreasing and bounded, then you know it converges. When it converges to, different story. Very different story. Okay. Growth rates. There are functions that are more complicated than the functions that we have dealt with. In particular, functions like the factorial function, n factorial. Anyone not know what n factorial is equal to? A few of you have not seen the factorial function. The factorial function, if you've had a stats class, you've seen it. So, or a probability class. So 6 factorial just means repeated multiplication down to 1. So that is 6 factorial. 3 factorial, 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2 times ... 3, 2, 1. So always repeated multiplication down to 1. And that function grows pretty fast. In fact, that function grows faster than an exponential function. But not as fast as this one. The one on the far right is the power tower. And that power tower grows the fastest of them all. Power tower flies. N to the n. So the ones that we are going to focus on, this growth rate table has some funny business in here that we don't need to get into. So we've got on the left the log function, and they raised it to a power. Log function grows slow, and if you raise it to a power, it still goes slow. So I've kind of summarized the ones that we're going to look at down here. And the double greater than symbol there just means polynomials grow faster than logs. Exponentials grow faster than polynomials. Factorials grow faster than exponentials. And power towers grow the fastest. So we're going to be looking at these ones right here. Those are the 5 primary ones. Log, polynomial, exponential, factorial, and power tower. And the reason that we need this growth rate argument is that we're not going to have access to L'Hopital's rule when we are dealing with, in particular, these ones. We don't know how to take the derivative of n factorial. It's possible, but it's really complicated. We can take the derivative of a power tower with logarithmic differentiation, but it's, we don't want to do that. It's too complicated. So when we are seeing factorials or power towers, we just are going to use the growth rate argument instead of trying to get into the specific details of how to take the limits. So here, when we take the limit of a sub n in this case, because the power tower grows faster than the factorial, that limit is 0. And similarly, if we were to take the limit of, if we were to flop it, go this way, as n goes to infinity, what would that limit be? Infinite. Right? That's going to be infinite. So here, when we're using the words, find the limit of this, here's where we'll use infinity. You could also say, if you wanted to use the word diverge, you would say this. You would say that sequence a sub n diverges. So slightly different context. How about this next one, 79? What about 79? What's that limit going to be? So we have a polynomial in top. We have an exponential down below. Exponentials grow faster than polynomials, so that's going to have a limit of 0. This could be n to the 5 billion. It doesn't matter. In the tail, the exponential will eventually take over, even if it is the smallest exponential function, 2 to the n. So long as that base is greater than 1, it's exponential growth. So if it's 1.1 to the n, it will eventually take over any polynomial, no matter what the exponent is. So here, limit of a sub n is going to be 0. Now, with both of these, we're going to want to qualify this. Like if we're doing this on a test, we would want to say something like this, by growth rates. So you just want to give some explanation. Now, if you can do the math, you do the math. But if it's got a factorial or a power tower, that's the one time where you don't have to do the math. You can just refer to the growth rates argument. That make sense?
Can you not use growth rates if it's the same on top and bottom?
Then you can't use growth rates. Then you can do some factorization and simplify it to something. If it's got the same nature, top and bottom, you can do some factoring, and you'll be able to break it down. Limit of a sequence. So we talked about this informally in 10.1, but here's the formal definition for a sequence to have a limit. And it's same definition that you used in Calc 1 for functions to have limits. So the sequence a sub n will have a limit of L when this stuff up here happens. And this can be a little bit tricky to understand, but let's go through it. So this first part up here, a sub n minus L. So first off, when you look at the picture, we've got our L right there. So L is going right down the middle there. And if you were to imagine what a sub n minus L is, a sub n minus L is just the difference between your sequence term and L. And so that's what this measures. This is measuring half of this dotted interval here, right? We've got this horizontal interval right there. These two horizontal lines, maybe I should call that a vertical interval, I guess, because it's on the y-axis. So this interval on the y-axis is 2 epsilon long, where epsilon above L, epsilon below L, and this just says the difference between a sub n and L is less than epsilon. You could be epsilon on the downside or epsilon on the upside. So that makes the interval 2 epsilon wide. So you've got this epsilon interval, this epsilon, it's like a tube, this epsilon tube. So that's going to be less than epsilon whenever n is greater than capital N. So that just says you're somewhere out, And if you're past this capital N, the rest of the sequence terms are going to be inside of this little epsilon strip, this little interval thing that's 2 epsilon wide.
And what's the purpose of it?
That's the definition of a limit.
Okay.
So that tells us, that's the formal definition of a limit. This says, and we're not going to do formal proofs in here. When you get into upper level math, you will, but here we're just trying to understand the concept. So the concept is that no matter, if this is true for every epsilon, then the limit is L. So the idea is that you start ratcheting down the epsilon value. First the interval is 1 unit wide, and then it's a half a unit wide, and then it's a quarter unit wide, and then it's a tenth, and then a hundredth, and then a thousandth, and then a millionth. If no matter how narrow you make this interval around L, if it's true that the rest of the a sub n's are inside that interval for some capital N out to the right, then the limit is L. So it's just got this ratcheting nature to it. If it's true, no matter how small you make this interval, you can go further out in the tail so that the tail is inside that epsilon interval, then the limit exists. That is the formal definition of the limit. But again, we're just sort of focused on the concepts here. We're not going to do proofs with limits or anything. All right, so recurrence sequences. We talked a little bit about those in 10.1. Talk a little bit more about them here. So a recurrence sequence, a recurrence relation, is when you find your subsequent term from the prior term. So in order to find a sub 10, you use a sub 9. In order to find a sub 1, you use a sub 0. So they have to give us a starting place, a starting value here. So we need that to start. And then we can find the rest of the terms by repeated substitution into this little recursive formula. So we plug the 2 in for a sub 0, and that will be to find a sub 1. So a sub 1, plug in this, and actually I have it right there. So we plug in the 2, we're going to have a half, and we plug in the 2 right there, we plug in the 2 right there, and we're going to end up with 1.5. So I started with a equals 2. Plug it in there, we get 1.5. So this is what the recurrence relation is generating. So that's our sequence. Our sequence is 2, comma, and then we have 1.5, 3 halves, and then we start getting into decimals. That one, the 6 is repeating, or at least it looks like it. Maybe I shouldn't write it like that because we didn't show that, but we'll just do this. And then 1.41. 1.414, repeat, or not necessarily repeating, but on and on and on. So that's our sequence. Yeah?
Why is this approaching square root of 2?
I don't know. Can you tell me why? You have no idea? So the question is, so we talked in 10.1 about recursive sequences, and if we are reasonably assured that they converge, so we look at empirical data, looks like it converges to some number, possibly square root of 2, then we can use this technique. So if we assume it converges, we do this. We assume that the limit of a sub n is equal to L. So if we assume that the sequence converges, then we can do that clever technique that we did on Tuesday. We take the limit of both sides of this. So we take the limit of a sub n minus a sub n plus 1. So a sub n plus 1 represents a sequence. And then we do the limit of the other side. So the limit of this. So we have that. And if the limit of a sub n is L, the limit of a sub n plus 1 is also L. They're essentially the same sequence. Although a sub n plus 1 has 1 fewer terms. Because n starts at 0. So if you think about plugging in 0 there, the first term in this sequence on the left is a sub 1. Whereas when you plug in 0 here, the first term of the sequence on the right here is a sub 0. So technically, a sub n has one extra term than a sub 1, or a sub n plus 1. But it doesn't matter because the limit of a sequence depends on the tail. You can chop off as many terms as you want in the front. It does not change the limit. So if you've got these two different sequences, their indices are slightly different. Doesn't matter. Their tails are the same. This is going to be L equals 1/2 times L plus 2 over L. The limit can distribute, and we get that. And so if the sequence does converge, this will tell us exactly what it converges to.
Will you do it the rest of the way?
Yeah, I can do the algebra. I'm confident. Super confident. So multiply both sides by 2, subtract an L, multiply both sides by L so that we get L squared equals 2. And we are going to choose the positive square root because these terms are all positive. So the negative option is not really an option. So that tells us that's why it converges to square root of 2. Because that's the answer.
Is that factor really like simpler than if it was distributed?
Say that once again.
So it's 1/2 times a sub n plus 2 over a sub n.
Mhm.
But if you distribute it would be a sub n over 2
Yep.
plus 1 over a sub n. Is
Yep.
that really simpler or more complicated?
It doesn't matter. You could do it that way easily. They'll be fine. It'll be about the same. We could do the same thing here and distribute the half here and get L over 2 and then 1 over L and then subtract the L from that side. It'll be the same. About the same in work. Yeah, so that's why the limit is square root of 2. Because it is. Because that's what the math shows us. Yeah, that's not easy to type into Desmos.
No, Desmos can do that.
Desmos can do all sorts of cool things. Okay, so looking here, again, it's recursive. We don't have a concrete way to just look at this and say, oh, it converges or diverges. What we have to do with recursives is look at the terms, and if we're reasonably assured that it converges, then the technique we just used will work. So you guys try this one. So figure out what that converges to. And it corresponds to infinitely nested square roots, which is kind of cool. No, nothing that complicated. Yeah, that would be an ask. That'd be mean. Anyone get the limit yet? Read two. Kurt, two.
I got it from bad.
Harrison, you get anything?
I got it from bad.
He's using his recursive method.
I use you sub, just kidding.
You use u sub. Don't use u sub. So the main idea is that we look at our empirical data. It's looking pretty cool. It looks great. Looks like it converges to 2. So we assume that it does have a limit, and then this technique will find the limit. So we're going to take the limit of both sides of that recursive equation. So we're going to take the limit of both sides as n goes to infinity. So on the left, the limit of that sequence, that's L. On the right, here comes some superpowers from the limit. Square root function's continuous. You can go right through it. So we can go right through the square root. You get that. Limit of a sub n is L. Square both sides. Subtract and factor. Is this where you got stuck, Harrison?
Never mind. Leave me alone. Connor's a terrible teacher.
He did more trash math, Jim.
Trash math?
Yeah, come.
I'm going to come and look.
No, because he tried to tell me to do it in a way where I was looking at it. Look at what he did. Look at what he did.
I got to say, this is public information.
This is
5 minus 1 is 3.
He subtracted.
No.
He subtracted L squared from L.
He did the square.
L squared.
L squared minus L is L.
No. You did the square root of L squared minus L, and it's equal to L minus the square root of L. This is what you tried to tell me to do.
It's a good thing he's in school.
This is why I was scratching out. I was like, how does that equal that?
All right, so everyone follow that kind of logic? Now this room, yeah.
You get no
Yeah. So the first step, the first step is that we're going to take the limit of both sides of this. We're going to treat it like an equation. So kind of like when we have an equation and we take the derivative of both sides or the integral of both sides or something similar, we're going to take the limit of both sides.
So for the first one where you say assume the limit of a sub n equals L, is that saying that a sub n is the explicit?
Converges. So we're saying that we've looked at data and we assume that a sub n converges to some random number L.
And a sub n is
Mine
the
does.
explicit?
No, it does not.
Yes, a sub n is the function that creates the sequence terms.
Okay.
Yep. So we're taking the limit of that function. A sub n is a function.
So why wouldn't it be the negative 1 at the end?
Because the terms are all positive.
Yeah, but if you plug in the negative 1, wouldn't it equal?
So this symbol right here means positive square root. But that's the principal square root. If you want a negative square root, you have to put the negative in front of it. If you see this symbol, it always means the positive square root. And there's some confusion there because in algebra, they don't always do that properly. You know, in algebra, you've got this thing, and you see all these algebra teachers do this, and then say x is plus or minus 2. That is wrong notation. That is not true. That is not correct.
Could you elaborate?
Yes, the square root of x squared is the absolute value of x. And the absolute value of x is going to be plus or minus 2. The absolute value of x is going to be 2. This symbol means the positive square root. And if you take the square root of x squared, you should be writing absolute x. The square root of x squared is absolute value of x. So it's better, and this is why most of us calculus teachers would prefer that algebra teachers would do this. And then conclude that x is plus or minus 2. That's what we would prefer. Because that is bad, that's wrong notation. It was wrong notation. So that symbol means the positive square root of 2. Doesn't mean plus or minus. Which is very easy to be confused on. This reminds me of a question. So somebody, you think in your brains here, tell me, I claim that this is an integer. I claim that's an integer. What integer? We hear 6? Anyone else make a guess? How many? Square root of pi? That's not an integer. So this is a lot like that rational thing where if you have a repeater, you can do basic algebra and figure out, that 0.3 repeating is 1/3. You can do the same type of thing here. If you let x
think it's 2.
equal this thing, and then you square both sides, this is one of those questions that you see on those, those tests, SAT tests, ACT tests. And then the square root thing is x. So then this becomes an algebraic equation. And then we do what we just did. You solve the algebraic equation.
And you can combine those x's, yeah?
So then we factor this.
When Carter said, I was like, what is he thinking?
And we get x is equal to 2 or negative 3, but it can't be negative 3 because, again, the square root's always positive. So that's just a really creative way to write the number 2.
Was that on your clock?
It might be. I don't know. I can't
In your
remember.
office?
Maybe. I gotta look. So the next time, oh wait, you guys don't write checks, do you? The next time you write a check, do this kind of square root thing.
I think the teller would assess me.
How would you do this with cash?
With cash, it's all green.
I mean, there is no $2 bill anymore, so I mean.
They don't make $2 bills anymore?
No? Really?
But they make pennies? The heck they making pennies for? Pennies.
Isn't it?
They should have gotten rid of pennies like 20 years ago.
Doesn't it cost more to make a penny?
Yes!
Than the pennies?
What kind of business is that? We're going to keep making pennies even though it costs 5 cents per penny.
You and a YouTuber, CGP Grace, shared the same opinion. Abolish the penny.
Abolish the penny.
Yeah.
You should have abolished the penny.
Hit pi is wrong. Just
So
kidding.
bad. Pi is wrong. Pennies are wrong. Okay, so let's go ahead and get into the series now. So now that we have growing pains, vocalized growing pains coming from the back of the classroom. Okay. So now that we know how to deal with sequences, now we're going to deal with series. So we're dealing with the hard part now. So focus. Focus. So we have, for a series, we start with a sequence of terms, and we want to add all of those terms together. So those are going to be added together. That's what forms the series. The series is the sum of this infinite sequence. So we've got that. There's our series. We say, there's lots of ways to say this. Usually we try to shorthand it. We'll say the series A sub n, or sigma A sub n, something like that. But again, we will just use the word series. We won't say infinite series every single time. And like we talked about earlier, we now want to build this auxiliary sequence called the sequence of partial sums. The secondary sequence. And this sequence of partial sums is found by doing this. We keep adding one more term, one more term, one more term, repeatedly. So this sequence up here is just this sequence with partial sums. We're going to partially sum the series. And then here is our big conclusion. If the sequence of partial sums has a limit of L, then the series converges to L, or the series equals L, however you want to phrase it. Doesn't matter. They mean the same thing. So the series is equal to L.
Does that work basically the same thing for product notation as well?
No. No. Product notation gets really messy. Like if you try to take the product of two infinite series, if you have two infinite series and you multiply them together and you form a product, that gets really
No, like with a capital Pi, do you have like a
gets
a
nasty.
series of partial products?
You can, yeah, you will, yes. Yeah, it gets really bad though.
What if you add series together?
So if you add series, that's fine because you can just add the terms that have the like index. Like, yeah, adding series are fine. They're just like it's just like adding functions or sequences. You just line it all up and you can add things. Adding is fine. If you add two convergent series, you will have another convergent series. Okay, so here is the most important series of them all, the geometric series. So the geometric series looks like this, and the sum of a geometric series is ever so simple. A divided by 1 minus r.
Where does that come from?
I shall show you. A is the first term in the series, and r is the common ratio. So when we look at this series down here, this series, A is the first term right there. Right? When K, usually with the geometric series, they like to start it at 0 so that this first term is just A. Right? A r to the 0 is just A. So your first term is A, and then r is the common ratio. R is what gets you from one term to the next. So you do repeated multiplication by r. So there's our geometric series. You can factor the A all the way to the front if you want. It can be in the front. It's common to all the terms. So the question is, when does it converge? Well, it'll converge inside right there. So when the magnitude of r is less than 1, which we've already talked about, if the magnitude is less than 1, you have convergence. And if the magnitude is greater than or equal to 1, divergence. So magnitude less than 1, converge. Magnitude bigger than 1, diverge.
How do you figure out what A is?
Yeah, we'll do some examples.
Okay.
So A is going to be the first term. We'll get
And
into
then that A over 1 minus R, that's how you find the limit?
that is the sum of the series. That's all you do. A over 1 minus r.
That seems very simple.
I know. It's so cool.
Uh,
So let me show you why it's so easy. So first off, this is the sequence of partial sums right here. So S sub n, do you all agree that this is n terms here? So remember that we're starting to count with 0. So if you wanted 5 terms and you started with 0, you would end with 4. Your counter would be 0, 1, 2, 3, 4 to get the 5 terms. If we start with a counter of 0, so the power on r in this term is 0, so the exponent on r is our counter, and that starts at 0, so we have to end, if we want n terms, we have to end at n minus 1 would give us n terms.
How do we have the right to put the equal sign there if it's an infinite series?
This is not infinite series here. Right? This is S sub n, which is the sum of the first n terms, so it's a partial sum. Right? This is just the first n terms added together. Right, so that's a finite sum right there. So that finite sum, it's an equation. We multiply both sides by r, and once we multiply both sides by r, we end up with this thing, and notice that if we do this subtraction right here, aren't we getting a bunch of cancellation? And we do that subtraction, these are all canceling. This term cancels. The only terms that are not canceling are that one and that one when we do this subtraction. So we end up with a minus ar to the n. Well, we have a common factor of s sub n here, so we can factor out the 1 minus r, divide by it, and this tells us what this gives us that formula for s sub n that we were talking about on Tuesday. It's not always easy to find s sub n. In fact, a lot of times it's impossible. But for a geometric series, it's easy. For a geometric series, that's what S sub n looks like. So that S sub n is true regardless of R. R could be 5. R could be -2. R could be a half. R could be a third. R could be pi. R could be negative pi.
What if R is a function?
R is a number. R is a common ratio. It's not a function. It's a common ratio. So this holds no matter what R is.
Will you ever, on the like test, give us like a really, really hard SN that's still solvable?
Because the only ones that we can for sure find S sub n on are going to be geometric or really easy. It's going to be, so no, unfortunately. So now, if this is S sub n, we know that the sum of the series is the limit of S sub n. So now let's take this limit. Well, we've already talked a bunch about this guy right here, this geometric sequence right there. R to the n is geometric sequence. We know that if we take a limit as n goes to infinity, that only converges if R is less than 1 in magnitude. So if R is less than 1, then the infinite series will converge. If R is not less than 1 in magnitude, then it diverges. You can still find the sum of the first 1,000 terms of a diverging series. Doesn't matter. But you can't find the infinite sum for a diverging series, only a partial sum. But if the magnitude of R is under 1, what does this go to? R to the n goes to, if R is less than 1, R to the n goes to 0. So this is going to go to 0 if the magnitude of R is less than 1. And if that's 0, then we're left with this simple little result, a over 1 minus r. So what we are going to see is that it's going to be a heck of a lot easier to add up an infinite series than a finite series. If you want to add up the first 1,000 terms of this series, that's a pain in the neck. Even if you want to add the first 10 terms, it's a pain in the neck. This r to the n term is a hassle. If your r is a half and you raise it to the 10th power, it gets to be really difficult. Whereas if you go all the way, infinite series, simple, a over 1 minus r. So that's cool. That's more is better here. All right, so let's actually look at one example before I do this slide. So for example, let's take a look at this infinite series.
That's a pretty sigma.
That's a pretty sigma. So let's suppose we have k equals 0 to infinity. And let's suppose we have something like, let's just make this 1/3 to the k. So that's a geometric series. We need two things. We need let me write out the first two terms just so you can kind of see it. So plug in 0, plug in 1, plug in 2, plug in 3. So 3 cubed, 27, etc. So that is our expanded form of that geometric series versus the sigma form or the closed form. Now tell me, what is A? First term?
1.
1. Tell me, what is R? Common ratio?
1/3.
1/3. Right? We're multiplying by a third repeatedly to get to the subsequent terms. 1 times a third times a third, a ninth times a third. So that common ratio is 1/3. We're multiplying by 1/3 again and again and again.
Is A usually going to be 1?
No. And so S is going to be this formula. So S in this case is 1 over 1 minus the third, which is 3/2. So that is the sum of that infinite geometric series.
Which is also the limit.
Yeah. It's the limit of the sequence of partial sums,
Okay.
which is the sum of the series. The limit of the sequence of partial sums.
So we don't have to use S of n?
No, we don't need it. We got rid of it. for a geometric series, the limit of S sub n is S, so we are right there. Now, if it said find the sum from 0 to 1,000, then we would have to use the S sub n formula. So, yeah, that's where we're going to go next, though. So we'll do a finite series in a minute. So one thing to be careful with are these indices. So let's just look at a specific example. Here we've got an S sub n, and I just picked A to be 1 and R to be 2. So this is the simplified form of S sub n. Now, does this geometric series, the infinite series, converge or diverge? If R is 2. If R is 2, it's going to diverge, right? R has to be less than 1 in magnitude in order for convergence. So we know that, bless you, we know that the series, the infinite series, will diverge. But regardless, this is what S sub n looks like. You can also see right there that it's going to diverge, right? 2 to the n as n goes to infinity is approaching infinity. So you can see it diverges there as well. Now the part you have to be careful with are these indices. When we say S sub n means the sum of the first n terms. So because we're starting at 0, this is the first term. We don't call it the 0th term. The S sub n means sum of the first n terms, so it's S1, S2, S3, right? So we just have to be careful that even though this index value up here, this index value is k equals 0 right there, k equals 1 right there, etc. This is the first term of the S sub n sequence. Right? The second term is going to be the sum of the first 2 terms. So we add the first 2 terms together to get 3. We add the first 3 terms together to get that 7. The first 4 terms to get that 15. So this is the sequence of partial sums. When we look at that, we also see, oh yeah, that diverges.
So then technically speaking, is the Fibonacci sequence a recurrence relation?
Yes.
Or
Because the subsequent term is defined from a prior pair of terms.
so
Yes.
so it is technically a sequence then?
Yeah, well, you know, the Fibonacci sequence is a recursive sequence. So we just have to be careful with indices. Indices can get super complicated when we're talking with series. All right, let's go ahead and take our break, and then we will do some examples of all these geometric series.
Whether your teacher matters.
But
All right, so let's go ahead and find the sum of some infinite geometric series.
It's a good time.
Or actually, some finite geometric series.
Yeah.
This infinite geometric series would what? Converge or diverge? Diverge. This infinite geometric series would diverge, right? Because both of those have an R value bigger than 1, 2, and pi. So those definitely would diverge.
Wait, but they wouldn't diverge in the finite time.
No, infinite.
Oh, okay.
Infinite.
Okay.
If it's infinite, it would
I was
diverge.
like, I thought these were finite.
Finite, yeah. The finite ones will converge for sure. So it's helpful to write this out a little bit just to see. So this is going to be the idea. And then it's going to go out. The second to last term, the k value is going to be 11, so we'd have 2 to the 11 plus 2 to the 12. How many terms does that series have? 8. No.
Well.
No. Who said 9? 9 it is.
6.
Does everybody know how to count?
No.
So let's look at this simpler one first. So let me say it this way. If k started at 1, then this number on the top would definitely tell us how many terms were in the finite series, right? What do you have to do to this k value down here to get to 1?
Subtract by 3.
Subtract by 3. So if you take the 12 and subtract by 3, you would get 9. So that's going to tell you that there's 9 terms. So that's one way to do it, is to think, what do I do to the k to make it a starting value of 1? So if you subtract 3 there, you subtract 3 there, and that tells you the number of terms.
Why 1, not 0?
So, because we start, well, usually if I'm counting apples, I start with 1, and then 2, and then 3, right? So when we're counting, we start with 1.
It's not our day today.
Okay, and so how many terms is this one going to have?
7.
If it starts at, if it's
7.
7! Because we have
6 in
to
programming
add one,
terms.
we have to add 1 here, we have to add
Still
1
alive, you're
there.
still alive, you're
Yeah.
still alive.
7, I agree, 7. 7.
But in programming terms.
Yeah, now programming.
Okay, yeah.
Okay, so now let's identify, so we have, in order to find the sum of this, so we are going to find S sub 9. We are finding the sum of the first 9 terms. So that subscript of 9 has nothing to do with what the index values are. S sub 9 means the sum of the first 9 terms. So we're going to add these 9 terms together. So there is our formula. Tell me what A is.
2 to the 4.
2 to the 4. We'll call it 16. Okay, everybody agree? A is the first term. There's the first term. Oops. There's the first term. That's A. Right there. That's A. Then we build our fraction, and we're going to have 1 minus r to the n. What is r?
2.
2. What is n?
Okay.
9. All divided by 1 minus 2. Okay, so this can be simplified. Let's see, 1 minus 2 is negative 1. I'm going to just push that negative 1 into the numerator and flop the order there. So we could write it as this. And did anyone type that into your calculator yet?
8176.
8176. So there is the sum of this finite series. Make sense? Make pennies? Any questions? Wait, question? Half a question?
Not really.
Yeah?
I can get it, I can get it.
Make sense?
What about 1, 1, 8, 1,
My algebra is
1, 8,
not
7,
helpful
6.
today.
Oh.
You get,
Here to here?
yeah.
So 1 minus 2 is negative 1.
Uh-huh.
If you
Oh.
divide by negative 1, it makes
I'm not good.
dividing by negative 1, is that really algebra?
Yes.
It can be. It can be. Yeah, okay, it's algebra. It's algebra today. It's algebra today. All right, next one. So let's not write out the expanded form here. Just look at it and think about A and R for a moment. All right, what do you think A is?
1.
I hear a 1. Does anyone else, you agree a 1? Carter, what do you think A is?
Yeah, 1.
Going 1. So, and everyone agreed that ratio is pi? Everyone agree with that? So the A is the first term, which is found with the first index value. Doesn't matter what the index starts at. Could be 0, could be 10, could be 5. Whatever the first index is, when you plug it in, that generates A for you. So A is always the first term. And now we are adding up how many terms? 7. So again, to get to 1 here, we added 1, so we have to add 1 up there. Another way to do that is to do the upper number minus the lower number and then add 1. That will also work. 6 minus 0 plus 1, 12 minus 4 plus 1. So you could do it that way. So now we use our partial sum formula again right there. So a is 1, and then we're going to have 1 minus pi raised to the n. We said n was 7 over 1 minus pi. So we get that. And there's not a lot we can do with that, so we'll just leave it there. So any questions on that? All right.
Could you also like convert the series so that k does equal 1?
Yes.
Still work?
That's a great point. So this is called re-indexing, and we don't have to do that. When you get into differential equations, you will have to do re-indexing quite a bit, actually. There's so certain differential equations you're going to solve with infinite series, and you'll want the powers of x to line up, and so you'll have to re-index. So here's how we re-index. We say to ourselves, what should k be replaced with so that this becomes a 1? So I want to replace k with an expression, and it's going to look like a tiny algebraic equation, but when we collect like terms, we want it to say k equals 1. So what do you think we're going to replace k with? K will be replaced with
A plus 1.
k minus 1. K minus 1. So now we come over to the series, and we're going to say, okay, all the k's get replaced with k minus 1. Well, this down here is an equation, and to simplify that equation, we're going to collect the like terms, i.e. the constants. And so we add 1. So now we've got that, and this is going to now we just have to make sure we get the upper limit right. We want to have 7 terms total. We know that this had 7 terms, so we're going to go from 1 to 7. So that would be a way to re-index it. So again, we don't have to.
It's more complicated the more.
Yeah, absolutely. But that is the idea, and we can do that for sure. Re-indexing. All right. So let me ask you about the infinite series first. Will the infinite series here converge or diverge?
Converge.
I think it'll diverge.
So the question is, what did you say, converge or diverge?
I think it's gonna
Converge. So we look at this number here, and if that number is less than 1, then it converges. E is 2.7-ish. Pi is 3.14-ish. So that's less than 1. So it's going to converge. So the common ratio here is E divided by pi. So if we come over here and do this as an infinite series, so if we have E over pi k, and let's just suppose we go from 0 to infinity. So this one is going to converge, and the sum of this is going to be a over 1 minus r. What would a be for this series? 1. So a is 1, because the first index value will give us 1, and the r is e over pi. So the infinite series will be 1 over 1 minus e divided by pi. And then we don't like complex fractions, so if we multiply through by pi, we would end up with this as our simplified sum. So the infinite series is a lot faster to compute the sum of. And there's a lot less thinking, because we have no r to the n. This r to the n is a pain.
And is this only if, it'll only be 1 if k is 0?
Yes. Well,
In most cases, is k gonna be 0?
geometric series often start with 0.
Okay.
But it's not, you can have a 1 even if this isn't, depending on what this algebraic expression is.
Okay.
It could be 1 even if that was not
And
0.
if 1a would be e over pi?
Say that again?
If k was 1, then a
Yes.
would be e over pi.
So good point. So if this k value started at 1, then a would be e over pi and r would be e over pi. Both of them will be e over pi. So over here, what about a in this finite series? E over pi squared, yep. So e divided by pi, quantity squared. So that's a. So how many terms are we adding together?
This is kind of unrelated, but
Yes.
would a constant be considered bounded?
Would a constant be considered bounded?
Yeah.
What do you mean?
Like y equals 2, is that bounded?
Yes, it's bound. It depends on what so when we go into two-dimensional space and we're talking about a function, that function will be bounded above and bounded below, yes. But it's not bounded in the graph sense of it. If you graph y equals 2, it's going to be a line that goes on forever and ever.
Right.
So in that sense, it's not bounded.
Right.
So the graph of y equals 2 is not bounded, but the function y equals 2 is bounded. So a function is bounded if it's got an upper and a lower, a floor and a ceiling to it. So it is bounded as a function, but as a graph, it's not bounded because we can't put a circle around it. Yeah. So the context is everything. So how many terms here?
49.
49. You can subtract 1 to get to 1. So you subtract 1 to get to 49. Or you can do upper minus lower plus 1. That also tells us. So we're trying to find the sum of 49 terms. Sum of 49 terms. And we know that that's going to be a, which is e divided by pi squared multiplied by 1 minus r to the n. So e divided by pi, and the n value is 49, over 1 minus r. We've got a complex fraction there. We need to simplify that at the very least. So we want to simplify this. The biggest denominator is e to the 49. So the best way to simplify this down is to clear that fraction. So we're going to multiply by pi to the 49 on top and down below. So if we do that, then we will eliminate the complex fraction. We'll no longer have complex fractions. So let's see. So we're going to have the e divided by pi squared. Let's just leave that alone. So here, multiply by pi to the 49, so we'll have pi to the 49 minus e to the 49, all divided by pi to the 49 minus e to the 48. So e pi to the 48. I can read your mind. There we go. So that's, that's better. If we're going to have any factoring here at all, we should either have no factoring or we should have as much factoring as possible. What's the common factor in the denominator that we could pull out to the front there? Pi to the 48?
Yeah.
So if we pull out pi to the 48, we're going to have pi to the 49 out in front. And then we're going to have this as our, kind of still pretty ugly. So that's going to be pi minus e. Yeah, so those partial ones, compare that to that, right?
Do we really need to simplify it if we throw it into a calculator then?
But we're not throwing it into a calculator.
But if we did?
But you're not going to be asked to. Oh, does it say to?
Yeah.
Normally, we want the exact answer. Normally. Yeah, this is one of those rare cases where they want us to round. So you're right. If that is what the question says, then we don't need to simplify. You're 100% right.
Wouldn't it be pi to the 50th since that first term is squared?
Yes, it would. Thank you. This is pi squared down here. So when we
No, you didn't.
Yeah, very good. I'm not going to type it into Des. You know how to type it into Desmos, right?
I'm kidding.
Why do you do that?
Just ask Siri.
Well, because then probably Siri would have a seizure.
Siri would not have a seizure.
Why are you looking at me?
No.
Just
I don't think Siri's that smart.
Yeah.
Yep.
Siri's too dumb for that. Then fighting words.
Yeah. Oh, I didn't do that though.
To some
I
extent.
forgot about that. Remind me next time.
I'm like, I
There's
asked
always
Siri
gonna
to
be
play a
someone
song.
that
And she's like, I'm
deserves
sorry,
to
I
pay a
can't show
penalty.
that to you when you're in the car. And I'm like, shut your mouth.
All right, so yeah, if you're ever trying to factor, Siri is connected to Wolfram Alpha, right? That's Siri's brain, and so you can have Siri factor 15-digit numbers. If you ask Siri to find the prime factorization of 345,542,000,000, she'll do it instantly.
Can you say that one more time?
But you know how Siri never hears you right, ever.
Precisely.
Yeah, so
Yeah,
there's
do it-
no
do
way
it
you'd
again.
ever get it.
Start her over. What is the prime factorization of 4,520,352?
The prime factorization of 4,520,352 is 2 times 2 times 2 times 2 times 2 times 2 times.
Holy crap.
She good.
I love that.
She's good. Yeah, that was great when they made that connection. Okay, so you all tried this one, 21. Infinite series. We have our simplified infinite series sum for a geometric series, so you all find the sum of that one. Yeah, she's a great factor.
Infinite Siri.
Infinite series.
How does it compare to Alexa?
She's way better.
Really?
More better.
She's more better.
It's not the fact that Alexa's way better for music.
Maybe.
I was really surprised when Siri heard what you actually asked her to factor.
Yeah, she's got pretty good ears these days.
Usually I ask her to play a song or something and she can't do it.
See, I have the same sense.
Depends on what the first index value is. So whatever that first index value is, when you plug it in and simplify it, it's whatever that is. So what will
Is it starting with 0?
well, the k value is 0. When we plug the k in 0, it's 140 0.
So it would be 1.
Yeah, so in this case, because it starts at 0. Because it starts at 0. So, in one word, algebra. What was the numerator? Denominator?
RB should be 1
So can't we separate that denominator into 16 times 4 to the n? Or we could pull 2 of the 4, if we pull 2 of the 4s off, pull
Yeah.
2 of the 4s off. You see it?
Makes sense, yes.
Yeah. You get your sum?
Well, it's just 1 over pi
So then simplify
to
that.
the end.
Yeah.
That looks like a number.
Why do you say that? Is
Because I don't have my
wrong?
glasses on.
You don't say that.
Right? So the R value is a quarter. A value is 1, because 1/4 of 0 is 1. So this S will be A divided by 1 minus R. That will end up being 4/3. 1 minus a fourth is 3/4. 1 over 3/4 is 4/3. Good? All right, here is one that's given to us in expanded form, but we can do the same thing. We can identify pretty easily that A is 1, And r is?
1 over pi.
Yeah, 1 over pi. So that's going to be our common ratio.
You have.
And so the s for this one will be a over 1 minus 1 over pi. Complex fraction, we simplify it by multiplying everything by the denominator of pi. So multiply through by pi, and we get that. Everyone okay with that? That didn't work out. Dude. I guess that's better. Alright. Alright, you all try this one. I want to see what happens to you. 30. See what happens.
Can we even use the same form? Wait a second. That's not fair.
I use this.
Mo better.
Oh, no, that's a 2. Oh. No, I see. Yeah, that is right. My hours aren't great.
I mean,
You write small.
I mean, I have this little space. But-
Right?
Yeah.
Yep, that's right. That's good.
Cool. Is this right for this one?
Let's see. What does that say?
I got a negative number.
That's impossible.
Yeah, check is. We'll go through it. Let's go
It's
through
possible. Probable.
it. Somebody tell me what A is.
5/4.
5/4. Agreed. Everybody agree? A is 5/4.
Super green.
Super agreed. What is R?
5?
Romeo.
Say again? 1/2. So if it's not totally obvious, then you want to write out terms. So if you write out your first few terms, when m is 2, you have 5 over 2 to the 2. What is the next term when m is 3? 5 over 2 to the 3.
Oh.
And then the next term, we'll just put one more term here, 2 to the 4, plus etc. So we see that it's actually only 1/2. When you're looking at this summand, that 5 is not wrapped up in parentheses. It's not being affected by the exponent, so it's not part of R.
So you could just, in a sense, could you just pull that slide
You could
out?
factor it all the way to the front if you want.
Okay.
Yep,
Immediately.
immediately.
So then it could just be 1/4 instead of 5/4?
Yep.
You just put the 5
And then you
out.
just have to multiply by 5 at the very end.
Okay.
Yep. So S is going to be A divided by 1 minus R. I'm going to multiply through by 4 to clear all the fractions. So that's 4. Canceling there, that's 4. That's going to be 2, so we get 5/2. Five halves. Any issues?
That last one.
The last one?
That's an issue.
There's an issue. So first, let's figure out if this is geometric. If we have an expanded form, it's not obvious that it's geometric. What is the multiplier that gets us from the first term to the second term? 3 over 4. So we multiply by 3 over 4. So we have to
3 over 4.
confirm that it's 3 over 4. That's just the first term. So is it still 3 over 4? Yeah. 3 times 3 is 9. And 64 times 2 is 128. 128 times 2 is 256. So geometric. The A value is a 16th. The R value is 3/4. So the sum is going to be A divided by 1 minus R. And that's going to be 1/4, I believe.
It does it in his head.
Do we agree?
Yeah.
So that infinite series obviously adds up to a fourth.
How do you write this with the sigma notation?
Oh, great question. So the sigma notation here, let's start at 0. For a geometric series, it's usually easiest if we start there.
But the first term isn't 1.
No.
Wait.
Moment. One moment. So that's kind of the standard geometric series form. It's called the arc
Yeah.
form, A r to the k, arc. If you start at 0, your A value will go here, your R value will go here, and then K is up on top of R. A r to the k. Yeah, that was a good question. Okay, let's go to that page. So here, we haven't done any with a negative ratio, but there's really no difference.
Can't you just factor it out?
We can't factor it out because of the power. So this power, that's a k, that's a power. It may not look like a power. That's supposed to be an exponent. So if there's an exponent on it, we can't pull it out. So if there's no exponent, like in this prior one, here you can factor out the 1/16. Here you could factor out the 5. But if it's part of the power, then you can't factor it out. So what do you think R and A are here? What is A first?
Is A just 1?
A is 1 again. Because we plug in our first index. The first index value is 0. Anything raised to the 0, other than 0, is 0. Okay, and then
0. Let's go.
R is -9/10. You agree? And our formula does not change. It's still S equals A over 1 minus R. So A over 1 minus a minus is plus. So we get that. And if you multiply everything through by 10, to clear that fraction, we would have 10/19. So that'll be the sum. All right, you all try the next one. You ready to do it?
No, I was saying
All right, zone in now. So everyone try this 36 one.
Didn't get mountaineering mount bindings to my skis.
Say that again, woohoo.
Didn't get mountaineering.
Yeah.
They'll do bindings to skis.
Yeah.
Chevy.
Yeah. Did you buy
Nice.
bindings?
That do what?
Have you bought them yet?
No, I'm just saving the credit card.
Yeah.
Ready
Really?
to go.
We don't have much longer.
I know. We're
Time.
doing a hut trip in January.
You are? Which
Yeah.
hut?
I have no clue.
Find out.
I'm going up blind.
Find out.
Okay.
Find out. I'm doing a hut trip in January too.
Oh,
Yeah, we're going to the Jackal.
how
Hut.
insane would that be?
That would be funny.
That would be insane.
Because I think we have half the hut, so the other half's open.
That would be sick.
I think we're going. Anything to the 0? I gotta look. Oh, I don't have my phone. I'm going to doing 2 in the spring.
Okay, I'll ask.
Yeah, find out which hut that is. That's.
Watch it be the same one.
Yeah, that'd be fun.
Just when I sprained my
Yeah,
ankle,
you're
Jim
tripping
can
out.
rescue me. Jim, carry me out.
So your R values are. When you're trying to find your R value, make sure that you're looking carefully. R is below K, not below negative K. So be careful with your R value. What's your R value?
Negative E.
No. Whew. Yes.
Or it'd be E because R, if K is positive.
So we want to rewrite this. Here's going to be your rewriting step. You want to have
R is negative. So it's gonna be
just a K in that exponent position. So that's how you rewrite it. You want to get rid of that negative exponent because you want the power to be just k. We'll find out right now. We'll find out. So the a value and the r value are actually the same here, right? When we plug in k equals 1, we get negative 1 over e, so that's a. And the r value is whatever is below k, and that's negative 1 over e. So s is going to be negative 1 eth over 1 minus 1 eth.
That sounds so weird.
I know.
Sounds like you're about to say the word ether. Maybe like, nope,
Oh.
I can't do it.
Wasn't yesterday World Ether Day? I think yesterday was World Ether Day. Because it's the anniversary of the first surgery that happened in 1879 or something. First time that they used anesthesia.
Oh, dang. Did
Yeah.
they wake up? That's
Not like that story I heard this morning.
Dang.
Someone waking up while somebody was taken out in Oregon. That sounds painful.
My brother woke up and he was on surgery.
Just make sure if you use this fractional notation with slanted fraction, then you should really put that in parentheses just so that it's clear as in the denominator.
And we have to simplify that on the test.
Simplify this?
Yeah.
Yes, because that's a complex fraction. You always want to get rid of complex fractions.
And how did you simplify that? You just
Multiply
multiplied.
through by e.
Echo.
So if you multiply the numerator by e and you multiply the denominator by e,
When I was born, I heard.
Which is 1.
which is 1. E eats.
I knew
E
it.
over e is 1.
I passed. I already knew the answer.
50% more like all that.
It's almost too easy, you know?
Okay, that's not helpful.
I didn't do good at
Freeze.
this either.
It all makes sense. All of a sudden, it all makes sense. All right, try this one. Try number 49.
Oh my
Try
god.
49 and see if you can find your A, find your R. Yes. Wolfram's not getting a grade. Wolfram already passed this class long ago.
What if I am Wolf?
If he is Wolfram, then why is he in the class?
All right, so think about getting your A, think about getting your R. It might help to write this in expanded form with big fractions instead of decimals. So try to rewrite it in expanded form with fractions. What is the first fraction going to be? Nope. Not three 1/100ths.
37 100?
Nope. 37 1,000ths. So that is the first fraction.
Oh, because I wrote my decimal.
That is the first fraction. What do you, anyone have the second fraction? 37 over?
100,000?
Over 1,000,000. Right, we have to do 3 more zeros. So we have to add 3 more zeros, so that's going to be a mil. Or 1,000 squared. Yep, 1,000 squared. Yep, that's 1,000,000. That's going to keep on going. So what is A? A will be
37 over 1,000?
37 over 1,000. And what will R be?
1 over 1,000.
1 over 1,000. So then S is A divided by 1 minus R. So 37 over 1,000. 1 minus R.
Could you write it in sigma notation, just so I can see what it would look
Yep.
that way?
Mm-hmm. So then we're going to multiply through by 1,000 here. And this is our final answer. So if we want to write this in sigma notation, the easiest thing to do is to write it in sigma notation from 0 to infinity, because then we just do A r to the k. We just do arc. We put in our A value, 37 over 1,000. There's A. And then we do R, which is 1 over 1,000 to the k. That'll be the simplest way to put it in sigma notation. Standard sigma notation, start at 0, A, R to the k. That's the easiest way.
So you would write it as 37 over 1,000 squared to the k?
Nope. This constant can't be merged with this power,
Oh, okay.
right? You can't get inside that base for that exponential expression. Okay, try this one, number 50.
K is for constant.
K is for constant, that's right. That's true. It's true. You already get it? Did you already get it?
I'm thinking on how to get it. You could do 1 plus sigma notation. Is that how you do it? I can't do that.
Yeah, that's exactly what I'm doing. Pull off the 1. The repeating part is the geometric part. The 1 does not fit the pattern, so you want to pop the 1 off in front and treat it as 1 plus a geometric series. Right, the 0.25 repeating is the part that's geometric. But the 1 is just an extra thing that adds together. And then did you add the 1 in there? Oh, there's your. Yeah, that part's all good. Then you have to add 1 in there, right? Because this is 0.25 repeating. So then there's the 1.
Okay.
So we're going to treat this as 1 plus
Yeah.
0.25 repeating.
That makes sense.
So we're going to treat this as 1 plus 25 100ths. And what's the next term going to be? 25
Over
10,000? 25 over 100 squared, 10,000? Etc. So the sum of this whole thing, only part of it is a geometric series. Let's write it in closed form here just to do it. All right, so what is A for that geometric series part?
25 over 100.
25 over 100. And then what is R?
1 over 100.
1 over 100. Everyone agree? 1 over 100. 25 over 100. So if we want to write this in geometric in this closed form, we could reduce a to 1/4 and then r to the k. So that's how we could write it with the sigma notation. And then let's go ahead and find the sum. So it's 1 plus a, which is 1/4, over 1 minus r. We're going to multiply top and bottom by 100. So we'll get that when we multiply it through by 100. We got that. And then we get a common denominator of 99.
124.
124 over 99. Comprendo? Ooh, that's bad Spanish, huh? Comprendas? Comprende? What am I supposed to say? How? What would I say?
You're asking what the group is entiende?
Oh,
Comprenden?
comprende?
Comprenden with an N.
Oh, comprenden. Comprenden. Okay. Question, Art?
So I started off with 1/4.
Yep.
So, but how is I supposed to know it's 25 over 100 instead of 1/4?
You can. I put 1/4 here.
But like,
So when you're building your original expanded form, it becomes 25 over 100. But if you reduce it, it'll be 1/4, which you can do. Okay, so we need to sort of pace ourselves through all these different types of series. The first one we have now done, the first important one, is geometric series. Now we're going to hit our second type of series, which is going to have a totally different type of method for finding its sum. Okay, so geometric, we're all done with geometric, a over 1 minus r. Now we're going to go to this really interesting type of series called a telescoping series. And telescoping series are going to incorporate some stuff that we've done in the past. There is one commonality with geometric, and that is that we can find S sub n. In this class, this is the only other category of series that we can find S sub n for. The only one. The only other one. So geometric and telescoping. They're going to be the only two for which we can find S sub n. Only two.
That looks like partial fraction decomp almost.
It sure does. We will definitely be doing PFD in this section. Okay, so with telescoping series, let's just notice why are they called telescoping? So let's just notice this, that if we were to write this out in expanded form, we first plug in the 1, and we're going to have 1/3 minus 1/4. That would be the first term, 1/3 minus 1/4, first term. The second term will be found by plugging 2 in for the k. So we're going to have 1/4 minus 1/5. The third term, we plug in 3 for the k, so 1/5 minus 1/6. And it should be apparent why we call this telescoping.
not really.
Those old telescopes that collapsed, right? They collapse. All these things are canceling. There's a ton of cancellation here.
But you can't collapse an infinite telescope.
Exactly. you have to find S sub n and take the limit. Exactly. Good point. That's exactly what he meant.
Why do I feel like I forgot the DX?
You never forget the DX.
Someone else?
All right, so
I didn't forget it on the test.
oh, you did good.
I had to.
You surprised me.
Okay.
Oh.
I wanted to know when he sat down my exam. He said, wow, you're actually kind of smart.
Actually has some skills. Okay,
He
so
would actually.
with geometric series, with telescoping series, we need to find S sub n. And it's going to be a little bit more complicated than for a geometric series. For a geometric series, it was pretty easy to find S sub n. We just needed A and R. So here, we're going to start by, this is the easiest case because it's starting at 1. All right? So S sub n is going to look like this. This term is the first term, so let's call that the term that comes from k equals 1. So S sub n counts the first n terms. If we start at 1, the last term is going to have a k value of n. So that's pretty easy. So this is going to be k equals 2. And we already said this is k equals 3. And so when we do these telescopers, we're going to leave a gap. And we need to get down to the last 2 terms in S sub n. Usually that's enough to see the cancellation pattern.
Infinity minus 1. Just kidding.
Keep your negative 112 to yourself. So the last 2 terms of S sub n are going to be k equals n minus 1 and k equals n. And since we started at 1, the nth term will be when k is n. So when we start at 1, easiest case, if we want to go n terms, we just go until we plug in k equals n. 1 to 5 terms, we go until we plug in k equals 5. So this is the simplest case. So if k does not start at 1, it's a lot more complicated. So k being n minus 1, we plug in n minus 1 right there. So n minus 1 plus 2, we get n plus 1. Minus, plug in n minus 1 right there. We get 1 over n plus 2. Now we get to k equals n. That's not too bad. We're just replacing k with n. So there we have our nth partial sum. Now we can do the cancellation type thing. We can see that, I'm not going to do it quite yet. So everybody agree that that's S sub n. That is the sum of the first n terms. But in order for us to take the limit of that, we need to simplify this first. So we want to be really careful what our cancellation pattern is, and it's pretty obvious here. I'm going to refer to this term as having a first part and a second part. So the second part of this term cancels with the first part of the subsequent term. And then we keep doing that. Second part cancels with first part. So when we're going left to right, second part cancels with subsequent first part. Now when we're going backwards, when we're going from right to left, so back over here, we have a slightly different cancellation pattern. Right? The first term here is going to cancel with the second of the prior. First term here is going to cancel with second of the prior, which is going to be somewhere in there. And then everything in the middle is going to collapse
So
down.
it's going to destroy everything except for the first and very last term.
In this case, yes. So in this case,
Wouldn't that be in every case?
no. It depends on the difference between the denominators.
Okay.
So there's a 1 difference between the 3 and the 2. So if it was k plus 2 and k plus 4, there would be 2 in the front and 2 in the back.
Okay.
Yep. All right, so S sub n can be simplified down to 1/3 minus 1 divided by n plus 3. So there is your S sub n. You will be asked to find S sub n. And then we find S by taking the limit of S sub n. And what is the limit of that? 1/3. So that is the sum of our geometric series. Telescoping series. Telescoping series. So with this first example, I kind of wrote out this general look of the expanded form just to sort of talk about the collapsing stuff. In practice, it's smart just to go straight to S of n, because then you don't have to do writing all that stuff twice. So let's leave this right here, and you all try 55. So write out S sub n, and then take the limit of S sub n. Find S sub n, simplify S sub n, and then take its limit. Daniel, we miss you. Yeah. He's not coming in today. Let me know if you're stuck on any piece here so I can give you a nudge.
Why did I write S over N just now? That's just so bad.
S sub n?
I wrote S over N instead of S sub N.
Sounds like -1.
Well, I know -112.
Sounds like a -1. Sounds like a red pen. Yeah, that's what your total will be. Yeah. What did you do? Where's your S of n? S of n. Oh, it's this whole thing. Yeah. So again, this one, these are the simplest when they start with a counter of 1 and when the denominators only differ by 1. That's going to be simplest case. All right, so S sub n, sum of the first n terms. We start by plugging in 1, so we get a half minus a third. And a lot of this stuff is going to be easier if you can keep track of your k values. And so if you put your k value below it just to keep track. Once we get to k's not starting at 1, it's going to be really easy to get your indices tangled up. So it's good to just be sort of neat. So the rule of thumb, when you're finding S sub n, the rule of thumb is going to be to find the first 3 terms and the last 2 terms. 1/2. So let's see. So again, because we started at 1, k equals n minus 1 and k equals n are the last 2 terms.
Special permission.
So all we have to do now to find this term is to replace the k up here with an n minus 1. So we're going to get 1 over n minus 1 over n plus 1. So for your S of n simplified, you should have 1/2 minus 1 over n plus 2. So there is S of n. All the other stuff in here is going to cancel out. That. All that stuff's canceling. And so then, obviously, S is 1/2. Yeah. So S is the limit of S of n, which will be 1/2. Not too bad? Should we up the ante?
Let's do it. We got 7 minutes.
We've got plenty of time to up the ante. Any questions on any of the steps? You got it?
Yeah,
Got it.
What be easy.
I'm not surprised.
Wow.
All right, now we see a log. This apparently is a telescoping series. Let's look. So what log property do you think we're going to use?
The subtraction one.
The subtraction one. So it's log of k plus 1 minus log of k. Okay. Let's take a look at S sub n. Again, we started at 1, so we're still dealing with the easiest case. The k and the n match. All right, so first term, log 2 minus log 1. Whoa, what just happened? Let's just do this. Will that do it? It shrunk. Everything shrunk. I gotta go to view and go to 100. Okay, we're back. So what is the first term in S sub n? What's the first term going to be?
ln2.
Yeah, you're still into.
ln of 2? All right. So we've got ln2 minus ln1. I'll just put it in there for the heck of it. So that's when k is 1. When k is 2, we get ln3 minus ln2. When k is 3, we get ln4 minus ln3, plus some dots. Now we have our k value, the two k values down here. So we have 1, 2, 3, and then we're going to have k equals n minus 1 and k equals n. So plugging in n minus 1, we're going to get natural log of n minus natural log of n minus 1. Plus natural log of n plus 1. Wait, should that be n? That should be n minus 1. Yeah, and then plug in n, we get n plus 1 minus natural log of n. Okay. All right, let's shrink it a little bit. Okay, any questions on how we got to each of these?
Okay, 0.
So we're plugging in k equals 1 to n. 1, 2, and 3 are pretty obvious. The two terms at the end should be k equals n and k equals n minus 1. So we're just replacing the k with n minus 1, and then replacing the k with n. And then we're going to look and see what cancels. So natural log of 1, that goes away anyway, but just leave it there to notice the pattern. So our pattern is really different. Now it's first part cancels with second part of subsequent. So first part cancels with second part of the next. This first part will also cancel with the second part of the next, which is somewhere here in the middle of the muck. There. And when we go backwards, if we look here for a moment, going right to left, second cancels with first of prior, second cancels with first of prior. So that's what we're going to do down here. Second cancels with first of prior, second cancels with first of prior somewhere in that muck. So the only two terms that are not vanishing are this one, which actually does vanish because natural log of 1 is 0, but from this point of view, it's a term that doesn't cancel. So what is the simplified S sub n then?
Negative natural log of n plus 1.
So this is 0, right?
Yeah.
And then we add that, so just positive natural log of n plus 1,
Oh,
right?
yeah.
Positive natural log of n plus 1. So this is S of n. That is S of n. And what about S?
Divergent.
Yep.
Good guess.
He's a great guesser. Yeah, so that series diverges.
Guessing is the right word.
Mm-hmm. Gets you like 50%.
So it diverges. All right, we're done. Ready for a weekend?
America.
Go carve some pumpkins.
Go cars.
Eat some pumpkin seeds.
Well,
Taste the chickens.
I think it's like.
Yes, you do. Don't go to Anderson Farms. Study.
Yeah. That's for later in the day.
Yeah, Anderson. Has anyone been to any haunted things yet? Have you already gone?
Go down Riverdale.
I took a Caltrito.
I don't drive on Riverdale Road. It's the most haunted road in Colorado.
Not anymore. I feel like it's definitely.
Oh, has it been exercise?
Yeah, no, not necessarily. Like, it's still just as crappy as before.
Yeah.
But there's so many more people that it's not as scary.
Okay, it's not as spooky because there's friends around.
Yeah, there's just so much more people. Like there's lights at one. I'm like, no, I just want to run into the tree.
I want to see the sign.